Okay, so last time we talked about an iterative method called Jacobi iteration, and then we see that under certain positive definiteness condition, the sequence generated by the Jacobi iteration converges. Right? So now what we are going to do is we are going to see an alternative condition for the convergence of such Jacobi iteration. So that is right, diagonally dominant right. So what we are going to see here is we are going to see the relationship between convergence and a certain type of matrix called diagonally dominant matrix. So first we will define what do we mean by diagonally dominant matrix. So right, so let Aij be an n cross n matrix. So you have components A11, A12, A13, all the way up to ANN. Right? So first row, second row, n rows. So it is a square matrix. Right, so we call that matrix A as a diagonally dominant matrix, strictly diagonally dominant matrix, if in each row the absolute value of the diagonal term dominates the sum of the absolute value of the off diagonal terms. Right, so that is right. So the meaning of this is the absolute value of the diagonal term dominates the sum of the absolute value of the off diagonal terms in each row. Right. Say for example, this is a diagonally dominant matrix. Right, so if you look at this matrix, in each row, absolute value of the diagonal term is strictly bigger than sum of the absolute value of the off diagonal term. For example, if you take the first row, diagonal term is 3, absolute value is 3, off diagonal diagonal terms are -1 and 1. When you take the absolute value and add them, you get 2. Right? So obviously 3 is strictly greater than 2. And same in all other rows as well. Right? So all rows has 3, 3, 3 on the diagonal, and that diagonal term dominates the sum of the off diagonal terms. So this type of matrix is called diagonally dominant matrix. So we are going to use this diagonally dominant matrix property to guarantee the convergence of the numerical method which we are working on. Right? So that is called the Jacobi method. Right? So before going into this, let me write down one exercise which we will do later, because that has something else with diagonally dominant matrix, but not with the convergence. So I am leaving it as an exercise because that is again you should have learned in the linear algebra. Right, so this is an exercise where you have to prove a strictly diagonally dominant matrix is non-singular. Right, so this has nothing to do with what we are doing now. So we will do it in a separate exercise later on. Right? But we will focus on strictly diagonally dominant definition and the convergence of the Jacobi method. Right? So I will write that as a theorem here. Okay, so this is the main theorem of convergence using diagonally dominantness of a matrix. So here we say that the Jacobi equation converges for any given initial value if the coefficient matrix A is a strictly diagonally dominant matrix, right? So we shall prove this. So basically you want to prove that the spectral radius of the integrated matrix is less than 1. Right? So that is what you wanted to prove. So let me prove that. right? So this is the first thing you have to notice, because you know that when we derive the iteration, we first divide by diagonal terms, right? To make sure that we are able to write A as I minus L minus U. So in that case, when you divide all the rows by the diagonal term, so every component in that row is being divided by AII. And then you split the lower triangular part separately and upper triangular part separately. So in the lower triangular part, you know that the upper triangular part is 0, and in the upper triangular matrix, the lower triangular part is 0. So that's clear. And so this is how your L and U will look like, right? Now, given that A is strictly diagonally dominant, so you know that right, but because A is strictly diagonally dominant, we know that AII, the diagonal term, is dominating the sum of off diagonal terms. So now combining both of them, we can derive the convergence. Right? So in order to do the convergence, we first see the Jacobi iteration. Right, so this is how we define the Jacobi iteration. Xk plus 1 is equal to L plus U. L is a strictly lower triangular matrix. U is a strictly upper triangular matrix times Xk plus C. Right, so B becomes C because you divide each row by the diagonal term. Right, so that's how you do this. So right, so the iterative matrix is L plus U, right? Right, so if you pick the ith row of the iterative matrix, you get minus, the first component in the ith row is minus AI1 over AII, second component is minus AI2 over AII, and all the way up to minus ANN over AII, and except on the diagonal term you will have 0, because you know L is a strictly lower triangular and U is a strictly upper triangular matrix. Right? the infinity norm of the matrix L plus U is basically the maximum row sum norm. Right? So if this is the ith row, maximum of the row sum for all I is summation of this plus this plus this plus this plus this. So it is summation of Aij over Aii. You know, when you put the absolute value, minus become plus. So it is a summation of j running from 1 to n, j not equal to I of absolute value of Ij over Ii, right? And this. Right? But from this, you know that, right? Right? From this, you know that when you divide by Aii, you get summation of Aij over Aii absolute value is strictly less than 1. Right? That is true for all I. Right? So this term within the brackets are always strictly less than 1. All the terms are less than 1. So when you take the maximum, you will get that is less than 1. Right? Therefore, therefore the infinity norm of L plus U is strictly less than 1 because it is maximum of a set of terms, all of them which are less than 1, so maximum will be less than 1. Right? So now you can go by two different ways. Right? One is when L plus U is rho of L plus U is less than 1, right? Because of the spectral radius property, right? Rho of L plus U is less than norm of L plus U. So then in that case, rho of L plus U is less than 1. And we already proved that in one of the earliest theorems, we proved if the spectral radius of the iterative matrix is less than 1, then the sequence converges. And so that is equivalent to rho of Nj is less than 1. Right? So then by an earlier theorem, this one converges. That is one way of doing that. Right? So if you don't want to use the earlier results, you can prove the convergence directly here. Right? So let me write down that as well. Right? Okay. So this is one way. The other way is right from here, you can directly prove that the sequence converges for any initial value, right, without using the earlier theorem. So in that case, you know that right, because you know Jacobi iteration is xk plus 1 is equal to L plus U xk plus c, right? But at the same time, you know this, right? You have x is equal to L plus U times X plus C. So if you combine, subtract one from the other, you get xk plus 1 minus x is less or equal to norm of L plus U times xk minus x, infinity norm. Right? So now if you continue doing this, right, so this is basically L plus U infinity square times norm of xk minus 1 minus x infinity, and if you continue doing this, you get norm of L plus U infinity to the power k plus 1 times x naught minus x infinity. And so in this case, you know that okay, so here you can easily see that because the norm of L plus U infinity norm is strictly less than 1, L plus U infinity norm to the power k plus 1 will goes to 0 as k goes to infinity. And in that case, we see that this whole thing goes to 0. So this goes to 0, and if this goes to 0, xk plus 1 goes to xk as k goes to infinity. And so that is other way of showing convergence without using the previous results. So here, what we do is we prove the convergence under the condition strictly diagonally dominantness of a matrix. As long as the matrix coefficient matrix A is strictly diagonally dominant, the infinity norm of the iterative matrix is less than 1. So in that case, either you can say spectral radius is less than 1, so the convergence is true, or you can directly apply the iteration of for convergence, and then you can show that because the norm is less than 1, the kth power of the norm will goes to 0, and hence the sequence converges. And so there are two ways to show the convergence. And so here, so far we talked about Jacobi iteration, and then in the Jacobi iteration, we see that how we can guarantee the convergence. One method is we see the positive definiteness of the coefficient matrix, and then the other one we see the strictly diagonally dominant property of the coefficient matrix. In both cases, we show that the sequence converges irrespective of the choice of the initial value. And so this is all about Jacobi iteration. So now we are going to see is, what we are going to see is, we are going to do the manipulation in a different way, right? So you know that A is equal to I minus L minus U. That is how we started, and then we keep I on one side and move L and U to the other side. Now what we are going to do is we are going to keep I and L on one side and move U to the other side and get a new iterative method, and we call that as a Gauss-Seidel iterative method. So that is the second type of iterative method which we are going to study here. That is called Gauss-Seidel iteration. this is called Gauss-Seidel method. So here what we are going to do is again we are going to start with Ax equal to b. Right, so this is the standard technique we use. First we divide by the diagonal term, right, to get Ax equal to b into I minus L minus u times h is equal to c, right? So that is the first step we do. And then what we do is we keep I and L together. Right? So we keep I minus L together on one side and move the u to the other side. So you get I minus L times x is equal to ux plus c. Now you multiply by the inverse of I minus L. You get x is equal to I minus L inverse u times x plus I minus L inverse c. Right, so this is in this way. Now what you have is you have x on one side and another x on the right hand side. So from this you can get an iteration. Right, so then we define the Gauss-Seidel iteration as xk plus 1 is equal to I minus L inverse u xk plus I minus L inverse c. So this is how we do the Gauss-Seidel iteration. Right, so here iterative matrices. The iterative matrix is I minus L inverse u. So that is the iterative matrix. So we define Gauss-Seidel iteration like this. But when it comes to computation, right, you notice that there is an I minus L inverse there. So every time when you compute, you have to multiply by I minus L inverse. So finding an inverse matrix is not easy in real computations, right? Even if you are using a computer to compute, it is not easy, it will take time. So we try to avoid multiplying by I minus L inverse in the computation. So we will see how we can leave that part and do a computation. Right, so I will write down this as a remark. Okay, so for the computation, what we are going to do is we are going to use the following version. Right, so here we multiply back by I minus L on both sides. Okay, so let me write the Gauss-Seidel integration first. So this is the Gauss-Seidel equation. So we multiply back by I minus L on both sides. So you get I minus L times xk plus 1 is equal to 2xk plus c. Right? So when you multiply, you get 2xk plus c. Right. So now what you do is you distribute this. So when you distribute this, you get xk plus 1 is equal to L times xk plus 1 plus u times xk plus c. Okay, so what you have here is you have xk plus 1 on both sides. You have xk plus 1 here and you have xk plus 1 here. But does that going to make trouble in computation? No, it is not. Because this xk plus 1 are associated with the lower triangular matrix. So because it is associated with the lower triangular matrix, when you do the computation, right, after you compute the first component, you can always update it to compute the second component, right? So here, the beauty here is it's because the xk plus 1 on the right hand side is associated with the lower triangular matrix. So the first component is required only to compute the second component. And then the first and second component are required to compute the third component. Right? And then again, the first, second, and third component are required to compute the fourth component. So only when you are computing a certain component, you only want the previous components, not the next component. So not any other components. Only the previous components are required to compute the present component within each step. So in that case, we can always update, right? So after computing x1 k plus 1, you can compute x2 k plus 1 and then so on, right? Here to get the computation done. So in that way, this method is useful in computation. So let's see first an example of how Gauss-Seidel method works, and then we will see the convergence of the Gauss-Seidel method. Let me write down the example. Okay, so first you are given a matrix system 3 minus 1 1 and minus 1 3 1 1 minus 1 3 x1 x2 x3 is equal to 3 3 3. So you know first you have to divide by the diagonal terms, right, to get this. So that's the first step I am going to do. 1 minus 1 third 1 third minus 1 third 1 1 third 1 third minus 1 third 1 x1 x2 x3 is equal to 1 1 1. Right, so you can first divide through by the diagonal term and make 1 1 1 along the diagonals on the matrix A. Then only you can write A as I minus L minus U. Right, so I can directly write L and U. Right, so my L is the lower triangular matrix 0 0 0 1 third 0 0 minus 1 third 1 third 0, and my upper triangular matrix U okay, and then U is this upper triangular matrix, so 0 1 third minus 1 third 0 0 minus 1 third 0 0. So this is your U and this is your L. So now you can write down the iterative method. Right, so 3 plus 3 matrix. Right, the whole thing. So that is okay, so after computing L and U, you can substitute that in the Gauss-Seidel equation and see the computation. So xk plus 1, because it has 3 components, I write it component wise so that I can explain you the multiplication here. And so xk plus 1 is equal to L times xk plus 1 plus u times xk plus c. C is 1 1 1. So this is how we write the Gauss-Seidel equation. So now you can see that first, if you want to compute xk plus 1, x1 xk plus 1, and to multiply this with this, so it's all 0. So xk plus 1 on the right hand side does not get involved in the computation of x1, right? So here the only problem is you have to do one by one. You have to do the computation component by component, right, in each step, right? So you can notice that so let us take the initial values are 0, 0, 0, right? So in that case, you know that these are zeros, 0, 0, 0, right? So in the first component, this first row multiplied by this is 0. So it has nothing to do with the computation. So right, so the first matrix multiplication gives all 0 multiplied by 0, 0. Second one again, this is this, but this is all 0. So when you multiply, you get 0 plus 1. So you get 1. So the first step, first component is 1. Then to compute x2, you know that you multiply the second row, right, by this. So you can see that 1/3 of x1 k plus 1 is there. Right, this. And then second row by this all 0, so you don't need to worry. It's 0 plus 1. So here to compute x2 k plus 1, you know that you have to use this x1 k plus 1. So you can compute that, that is 1. So you get a 4/3. Similarly, you can compute x3 k plus 1 as well. When you multiply x3 k plus 1, you know that you get minus 1/3 x1 k plus 1 and then plus 1/3 x2 k plus 1 and then plus this is all 0 and then plus 1. So you can do this computation. Right? So it is 4/3 plus 1 plus 4/9. Right? So do the calculation and you can simplify that. Right? So this is how you do the computation in Gauss-Seidel equation. Right? So here the biggest difference is here you have to do component wise calculation, and in the Jacobi equation you do all solutions, or you can compute each vector at each step, all the components parallel. But here you have to compute sequence. Right? So that is the main difference. write that as a remark. So this is the important difference between Jacobi and Gauss-Seidel, right? So in Jacobi, components are computed parallelly, but here in Gauss-Seidel, right, we have to compute sequentially, right? One after one only you can compute, right? So that is the big difference we have between Gauss-Seidel and Jacobi. So next, before going into the convergence of Gauss-Seidel, what we are going to do is we are going to generalize the Gauss-Seidel into a generalized method, and then we will look into the convergence of that generalized method, so that the convergence of that Gauss-Seidel become a special case. So let me introduce the method here, and we'll talk about the convergence in the next class. Right, so this generalized method is called successive over-relaxation method. Right. So here, what we are going to do is we are going to introduce a new variable inside the method. Right. So this is how we do. So here, you know that everything is same. Right. So you have ax equal to b. From this, you know, I minus L minus U times X is equal to C. That is what you have, right? So what you do is you multiply by an omega, right? Right, so what we are going to do is we are going to multiply both sides by an omega. So we get omega x minus omega Lx minus omega ux is equal to omega c. Or you can say W as well. This is omega, right? So when you multiply both sides by omega x, right? So omega x minus omega Lx minus omega, right? Ux is equal to c. From this, what you do is you do a little manipulation. Okay, so what you do is you just do a little manipulation. So you write it as okay, so you do a little manipulation, right? What you do is you keep the omega x Lx on one side, right? And then move everything to the other side. So you get omega c plus omega ux minus omega x, and then add an x on both sides. So that is what you do here, right? So once you do that, you will get this. So from this, what you can do is I minus omega L times x is equal to, right, 1 minus omega times I plus omega times u of x plus omega times c. So you get a new formula, right, with I minus omega Lx plus 1 minus omega times I plus omega u times x plus c. So then you can write the equation as this. The xk plus 1 is equal to I minus omega L inverse into 1 minus omega times I plus omega u xk plus I minus omega L inverse omega c. So this method is called successive over relaxation method. Right? So this parameter omega which we introduced here is called over relaxation parameter. Right? So you can see that when you put omega is equal to 1, you can easily see that this is same as Gauss-Seidel iteration. Right? So that is why I told you earlier that this is a more generalized method of Gauss-Seidel iteration. So in the next class, what we are going to do is we are going to see the convergence of this successive over relaxation method, so that in that results, by putting omega is equal to 1, we can always obtain the convergence of the Gauss-Seidel method as well. So in the next class, we will talk about the convergence of the successive over relaxation method. Right? You can, as a homework, you can easily check that putting omega is equal to 1 gives you the Gauss-Seidel method. Right? So this is the third type of method which we are studying. It is actually similar to the Gauss-Seidel method. Right? So the rest we will see in the next class.